Gas law number 5. On our way to 9. Although the first 4 were pretty easy. Okay. This is Dalton's law of partial pressures. Okay. Same Dalton. Same Dalton. In fact, is coming to explain this law. Adams explained this law. Okay. It's Adams that explained this law. But this is what Dalton found. He found that the total pressure inside a container is equal to the sum of the partial pressure due to each gas. Okay. So sum is a math word. What mathematical operation are we talking about when you say sum? Addition. So we're talking about addition. No, it's not integral to what we're doing. It's kind of derivative, actually. But no, that's the limit of the jokes we can tell. You see, math jokes. I can make math jokes too. Okay. When they say the partial pressure of a gas, what they're talking about is the pressure caused by that gas. So right down this room, the air is made up of 80% oxygen and 80% nitrogen, 20% oxygen. Okay. There's pressure caused by oxygen molecules hitting us. That would be the pressure caused by oxygen, the partial pressure of oxygen. There is pressure caused by nitrogen hitting us. That would be the partial pressure of nitrogen. And the total pressure would be the pressure of all the molecules hitting us. That would be the pressure of the oxygen plus the pressure of the nitrogen. That's what this law says. Okay, it's a really simple law. It makes perfect sense. Actually, atoms explain it. That's why Dalton did it. Atoms explain it because nitrogen atoms hitting versus oxygen atoms hitting. Well, he didn't know they were really molecules, but particles hitting explains this. Okay, here it is as an equation. Let's go with the complicated equations. P total equals P1 plus P2 plus P3 plus... When do I stop adding gases? When I run out of gases. Okay. So if you don't want to write that much, you can write, what was it? PT equals the sum from I equals 1 to n of P sub I. Oh. Okay. Just, okay. Well, some of you get that. Okay. Yeah, stuff's coming. Okay, so 4 containers. Green atoms bouncing around. Orange atoms bouncing around. Blue molecules bouncing around. 4th container. All the greens, all the oranges, all the blues. So the pressure in the 4th container can be found by adding up the pressure in each of the first 3 containers. If the first container is 2 atmospheres, and the second is 1, and the third is 3, what is the pressure in the 4th container? 6 atmospheres, because 1 plus 2 plus 3 is 6. And it makes sense, too. The collisions in that last one would be all the collisions you had in the first one, plus all the collisions you had in the second one, plus all the collisions you had in the third one. What Dalton's law is saying is you can pretend that the other gases aren't there. Like they don't take up any space. Right? Okay. So, okay, that means we can treat gases in the same container as if they don't affect each other. So I can find the pressure of oxygen and nitrogen separately from each other. And if I squeeze the container, I can find out how much the oxygen changed separately from how much the nitrogen changed. Okay, so you can figure their pressures out separately and then add them up. And then just add them up. Okay, so if you got those pink papers, what's coming up is, I'm thinking, number 9, number 9, number 9, number 9. And the Beatles, Revolution number 9. Okay, what is the total pressure in a balloon if the pressure of the oxygen is 170 millimeters of mercury and the pressure of nitrogen is 620 millimeters of mercury? Yeah. No work, no credit. Okay, so I get to crack that open and look what I want to grade it? Okay, so they gave me a pressure. They gave me another pressure. They gave me no other information. Anybody know, and they asked for a total pressure. Anybody know an equation that has those pieces in it? Dalton's Law of partial pressures. P1 is going to be the pressure of oxygen plus the pressure of nitrogen, which is 170 millimeters of mercury, plus 620 millimeters of mercury. My calculator says 790 millimeters of mercury. Is my calculator right? Well, 170 in the tens place is my last sig fig. 620 in the tens place is my last sig fig. So in this, I should have something in my tens place. So that's the right sig figs. Adding sig figs, the nasty ones. We've got to line them up. Okay. Really hard? No, let's make it harder then. Oh, it never gets really hard. Okay, in a second balloon, the total pressure is 1.3 atmospheres. If the pressure of nitrogen is 720 millimeters of mercury, what is the pressure of oxygen? Okay, so they gave me a pressure of nitrogen, they gave me a total pressure, and they asked me for the pressure of oxygen. Anybody think of an equation? Dalton, so P total equals P1 plus, or PO2 plus PN2, except this time I'm trying to find PO2, right? So the pressure of O2 is going to be the total pressure minus the pressure of nitrogen. So that is 1.3 atmospheres minus 720 gets you negative 719. And that tells you something's wrong. Because can you have negative pressure? Negative pressure means less than zero hitting. There is no negative pressure. Okay? There is no sucking. It's not negative pressure. No, there's no sucking. Because that would be negative pressure. There's no such thing as negative pressure. There's only positive pressures. Okay? So why can't I do this? Because I don't want to use 720, because 720 has the wrong units. So I got to take my 720 millimeters of mercury, get rid of millimeters of mercury, and change it to atmospheres. And 1 atmosphere was 760 millimeters of mercury. And 720 has 2 sig figs. The 760 is unlimited because it's a definition. And with 2 sig figs, that's 0.95 ATM. So 1.3 minus 0.95 ATM is 0.4 ATM. Because 1.3 minus 0.95, my calculator gives me no, it's actually 0.5, sorry, 0.5. My calculator gives me 0.45, but rounding, the 1.3 is in the tenths place, the 5 is in the hundredths place. I've got to round it off at the tenths place. Okay. 1.3 minus 0.95 gives me 0.45. What, 0.35? Oh, 0.35. Yeah, 0.35. Okay, that's 0.4. So it's 0.4. Yeah. Point. Yeah. Okay. Well, but one in the tenths place because of adding sig figs, subtracting sig figs. That makes sense. We lose a sig fig when we subtract this time. Because when I do the subtraction, 1.3 minus 0.95, get 0.35, but last sig fig is here. This one's here, so furthest to the left, I got to round it off here. 0.4 is your answer. Okay. Now, did I have to do it in atmospheres? No, I could have done it to millimeters of mercury. I could have taken the 1.3 atmospheres and turned it into millimeters of mercury and then subtracted. That would have worked. Because I could use either one because they didn't tell me what unit they wanted pressure in at the end. Okay. If they tell you what unit they want at the end, you change it to that one. Unless you love changing stuff. Okay. Where does Dalton's law get used most often in chemistry? Where it gets used in chemistry class is in collecting gases. And we've collected gases before. One with the sink, we did that. And when we did the butane lab. You were talking about the rocket lab. We did that. And the butane lab, right? Both of those, we did that. And when we did that, both time, in order to trap the gas, we collected it over water. We bubbled it through water and collected it. That causes a minor problem. And that minor problem is water evaporates. Okay? So as soon as you make that empty space up above by making bubbles, the water at that surface is going to evaporate into that empty space. So that the container has a pressure, but that pressure is caused by both the gas that you bubbled through and by the water that evaporated. So there's one specific partial pressure that we run into very often. That's the partial pressure of water vapor. That is called the vapor pressure of water. Okay? So in order to find the pressure of the dry gas, that means the gas without the vapor, you have to subtract the vapor pressure of water. Which means you would have to know the vapor pressure, the pressure caused by water vapor. Luckily for us, there's a table. You don't have to memorize it. There's a table on page 899, on page A8. Table A8. Okay. I'll show it to you here in just a second so you see what we're talking about, since I have the book online. Okay? So here's what it looks like. If you go to that table, see the top of it. So it says water vapor pressure. So that's pH2O. Okay? And as you can see, it started 0 because that's when it starts to be a liquid and starts evaporating. It doesn't evaporate very well because it only makes 0.46 millimeters of mercury pressure. And that gradually grows. As you go, actually it does 0, 5, 10, 15, and from 15 to 20, 25, they go by half a degree. Because those are right around room temperatures, ones you're going to run into all the time. Okay? And as you watch, half a degree, half a millimeter of mercury, 6 tenths, 6 tenths, 6 tenths, 7 tenths, 1.5. Oh, that went up a whole degree. But 1.5, that's more than twice as big, right? You get down over here, from 40 to 50, it goes up less than 40. But from 50 to 60, it goes more than 50. And from 80 to 90, it goes up 170. And between 90 and 100, it goes up over 200. And look at where it ends up at. 760. Okay, 760 is 1 atmosphere pressure. Okay, it's also and 100 degrees Celsius is the boiling point of water, and it's the boiling point of water because that's the vapor pressure. Think about what it takes to boil water. You have to make a bubble underneath the surface of the water. Now, if you make a bubble underneath the surface of the water, that water has to lift up because that bubble is going to take up some space. So in order to make the bubble here, you've got to push the atmosphere out of the way on the top of the water. The atmosphere stops fighting you. Those collisions on the surface are trying to stop the bubble from happening. Okay? So that when you first form bubbles at the bottom, well, the second time. The first time you heat up water, the first bubbles you see are dissolved gases. And then you start to see bubbles that form on the bottom and rise a little bit and then collapse. And that's because at the bottom they're at 100. They rise up, they run into some colder water. They're not at 100 anymore. They can't fight the atmosphere, and they collapse. And that's the noise you hear when water boils. You're hearing collapsing bubbles. Finally, when you get it up to all the water up to 100, that bubble can rise all the way through and reach the surface without cooling down enough that it collapses. So water boils when the vapor pressure equals the pressure you're putting on it. Okay? So that's why 1 atmosphere is 760. Why the vapor pressure of water is 760 at 100 degrees, because water boils at 100 degrees. So that's when the vapor pressure equals the external pressure. Okay? But what you need this for is to look up numbers. Okay? You don't have to memorize it. You just have to be able to look it up and remember to go look at it. So okay, so got a sample of gas collected by water displacement, where we bubble the water into the flask and to push the water out of the way. Water displace. We displace the water with the bubbles. Okay. The atmospheric pressure is 757 millimeters of mercury, and the vapor pressure of water is 17 millimeters. What's the partial pressure of hydrogen? So apparently the gas we collected was hydrogen. Under the conditions of STP. Did I skip a question? Yeah, okay, there we go. That's the wrong one. Yeah, atmospheric pressure is 757, the pressure of water is 17. What is the partial pressure of hydrogen under these conditions? Well, the total pressure equals the pressure of hydrogen plus the pressure of the water. Right? Apparently got 2 kinds of gas in there. So that means the pressure of the hydrogen would be the total pressure minus the pressure caused by the water vapor, the vapor pressure of water, And that is 757 millimeters of mercury minus 17 millimeters of mercury gets you 740 millimeters of mercury. Sig figs wise, it should be 7.40 times 10 to the second, because I want that 0 to count, because the 7's counted. So that 0's got to count, because it's in the same place the 7's were, and we're subtracting. Oh, units, millimeters of mercury. Hugely different than what we did before? Okay, so, right spot. Okay. So oxygen gas is collected over water. So I've made some reaction that made oxygen. And I collected, the water was at 25 degrees Celsius, and there was a pressure of 1.02 atmospheres. The total volume of gas collected was 293 milliliters. What volume of oxygen would be collected at STP? Okay, so 25 degrees Celsius is the temperature. 102 atmospheres is the pressure, and it's the pressure, it's the total pressure. It's everything. That's the volume. They ask for a volume. They want volume 2. So that must have been volume 1. And that total pressure was P1. And the temperature there must be T1. You say, well, that means I need a T2 and a P2. I have them right here. That's T2 and P2. The temperature at STP is 0 degrees Celsius. The pressure is 1 atmosphere. Right? Okay. So I have all sorts of numbers. Where do I need to start? Well, they want the oxygen at STP. So I need to start talking about oxygen by itself first. And my pressure at the beginning is not oxygen by itself. That's its pressure plus water. Does that make sense? So I need to start off with that 1.02 atmospheres. And I've got to subtract the vapor pressure of water to equal the pressure of the oxygen. How am I going to find the vapor pressure of water? I've got to check the chart. What do I look for on the chart? 25 degrees Celsius. Okay? Because at higher temperatures it evaporates faster because the molecules are moving faster. So at 25, they don't give it to me in atmospheres. They give it to me in millimeters of mercury. 23.8 millimeters of mercury. But I can convert that to atmospheres. Or I can take the 1.02 and turn that to atmospheres, or turn that to millimeters of mercury. But either way would work, as long as they're the same. Because I got to change millimeters of mercury to atmospheres. 1 atmosphere is 760. I get 0.0313. 3 sig figs. The 0 in fronts don't count. ATM. So I subtract 0.0313. I'm going to put a 0 there. And I get the pressure of O2 is 0.99 ATM. I know they both start off with 3 sig figs and we only end up with 1. That's because we subtract. And we lose a sig fig along the way. I got to keep 2 decimal places. Okay, so there's my pressure of O2. So now that's my P1. I got my V1. I got my T1. So I need to go to PV. So I need to use the combined gas law. P1 V1 over T1. Temperature's on the bottom. P2 V2 over T2. And I want to solve this for V2. So that means I'm going to multiply both sides by T2, divide both sides by P2, and I end up with P1 V1 times T2 over P2 T1. So V2 equals T2. What temperature is T2? It's 273 Kelvin, because it's STP, 0 degrees Celsius. P1, 0.99 atmospheres. I want just the oxygen. V1, 293 milliliters. Over P2, what's the pressure at STP? 1 atmosphere. And T1, 298 Kelvin. Got to add 225 and 273. Because that's everything, and I want just the oxygen. Right? I want the volume of oxygen, so I want to use the pressure of oxygen here, not the whole pressure. Because my original container had oxygen and water in it. I had to subtract away the water. Make sense? Okay, original container, bubbled gas, oxygen and water causing pressure. I want to know the pressure caused by just the oxygen. I want to know the volume of just the oxygen. So I need to subtract away the pressure caused by water. That's where I got the 0.99. And I'm looking for the volume of just the oxygen, so I'm going to use the 0.99 as just the oxygen. Push all those buttons. 273 times 0.99 times 293 divided by 298. And you get 270 with 2 sig figs because of the 0.99. 1 ATM is the definition. Right? We didn't measure it. We said STP is 1 atmosphere. Somebody picked it. It's absolute. And that is what units? Well, the kelvins cancel out. The atmospheres cancel out. And I'm left with milliliters. Yeah, I got it. So sometimes you have to fix your units along the way. Do a little subtraction. And then they ask you questions like this. Okay, this is what's written for number 12, or 9, 10, number 11 on your paper. There are 2 containers connected by a valve. One holds 4 liters of nitrogen at 2 atmospheres. The other holds 2 liters of oxygen at 8 atmospheres. The valve's opened. What's the pressure of nitrogen? What's the pressure of oxygen? And what's the total pressure? So here's what we're talking about. 4 liters at 2 atmospheres, 2 liters at 8 atmospheres. I turn the valve, it opens, and the pieces can now move around. And now the nitrogen's in the oxygen's in the nitrogen. So what is the pressure of nitrogen after I open up the valve? That's what we want to know. Well, what do I know about nitrogen? Well, there's V1, there's P1. I'm trying to find P2, so I need V2. So what volume do I get when I open up that valve? They can go anywhere in there, so it's now 6 liters. Right? Because it could be anywhere in the whole container now, so that's a total of 6 liters. So I got P1, V1, and V2. I can find P2. P2 equals P1, V1 over V2. 4.0 liters times 2.0 atmospheres divided by 6 liters. And that's 8 divided by 6, that's 1 1/3, that's 1.3 atmospheres. So when I open up the valve, the pressure of nitrogen would drop because it's got a bigger container. What about oxygen? Well, V1, P1. What's V2? For oxygen, once I open up that valve, it's 6 liters. It can be anywhere in that container. So that was my N2. For O2, it's P2 equals the same equation, 2.0 liters times 8.0 atmospheres divided by 6.0 liters. That's 16 divided by 6. That's 2 2/3. That is 2.7 with 2 sig figs. And the units are atmospheres. So I'm just doing Boyle's law problem, ignoring the other gas, because Dalton says it's okay to pretend the other gas isn't there. And the total pressure is the pressure of nitrogen plus the pressure of oxygen, which is 1.3 atmospheres, plus 2.7 atmospheres, gets you 4.0 atmospheres. You notice that the final pressure is in between the highest and the lowest pressure. The word for that pressure is actually geometric mean. Instead of our arithmetic mean, it's the geometric mean. No, you can't. You can't be mean like that, Mr. Green. Oh. It's Friday.
Or the highest point. Yeah.
Have a good weekend. Hope to see you Monday. I'd rather be here. Because you say learning's bad. Learning by yourself is badder.
And it's like, some people like are being pulled on all our teachers. We still have to wake up at the same time and be there.
No. I picked 10 o'clock.
No, yeah.
I picked 10 o'clock. I'm not doing it during class time. You guys are teenagers. You can wake up later. 10 o'clock, 10 a.m. I did not pick a 7 a.m. start time. I may be starting at 7 because I'm used to it. Yours, I said later in the day, because. That's right. Yep. Yeah. You didn't have time yesterday. You guys have to do the lab, or.
Just like because yesterday you weren't here.
But the sub said to do. I told the sub to tell you to do the lab.
Oh, he didn't talk to us about it.
It was a she that I saw.
Oh, she, yeah.
Yeah. Okay. Well,
Could I get gas law practice?
I'll get you gas law practice number 1, and we'll do this if we come back on thing. I won't hold it against you. Okay. But I got to go take care of some stuff. Number 1.
Thank you.
Yep. Red dress.
Morning, Mr. Green.
Morning. It's still morning. I'm in morning because I didn't get. Yeah, it's morning somewhere. It's always morning somewhere.
Yeah.
Hello. Maybe she shows up more than you. I'm thinking that's going to be a huge part of your grade in water polo, right? Well, if you sink, sinking would probably ruin your grade too.
Brent Coda, please report to the records office. Brent Coda, please report.